In this video, we are talking about finding the rate of growth or decay from exponential functions, and then we're going to do some mixed examples that you might see on an exam. So in the first 4 examples, we are just focusing on finding the rate of growth or the rate of decay. All right, so remember that for our exponential function, it's y equals a times b raised to x, where a is your initial value, b is the base, and that base can either be greater than 1 or that base can be between 0 and 1. If it's greater than 1, that represents growth, and if it's between 0 and 1, that is decay. Okay, so in example 1, what is our initial value there? Well, the a is 2 because it's the number in front of the parentheses. The base is the number that has the exponent, which is 1.19. And since 1.19 is greater than 1, that represents growth. Now we want to know what is the rate of growth. So by what percentage is that function increasing? To find the growth rate, you're going to do the base minus 1. To find the decay rate, you're going to take 1 and subtract the base. So to find your growth rate, you're actually going to subtract 1.19 minus 1, because remember, when we had our base, this number actually came from taking 1 and adding that rate as a decimal. Remember when we had to add that r when we were given the rate sometimes? So now we're kind of working backwards. We already have the 1.19, and we want to go backwards to see what was that rate that we had to add to 1. So we're going to subtract 1.19 minus 1, and that gives us 0.19. But we want this to be in a percent. So remember when we had our percent, we had to divide by 100 to get the decimal. Now we're going backwards, so we have to multiply by 100, which is 19%. Okay, in example 2. Our initial value, the a, is 4. The base is 0.89. And since 0.89 is between 0 and 1, that represents decay. Now, in this case, we want to know what did we do to get 0.89. So really what we're asking ourselves is, what did we have to subtract? We had to do 1 minus something to get there. What was that percentage that we have to subtract? All right, so to find this, we're actually going to do 1 minus 0.89. And that's going to give us that percentage that we had to subtract for the rate. So 1 minus 0.89 is 0.11. Now, as a percentage, we're going to multiply by 100. And that gives us 11%. Okay, so if you're ever concerned that you're doing these incorrectly, you can always check by saying, well, if my decay rate was 11%, that would mean that I had to do 1 minus 0.11, and if that gives me 0.89, then we're good to go. All right, in example 3, this one's written a little bit differently, but we can make it look like y equals a times b to the power x. So 2 is what has the exponent, so that is the base. So if our base is 2, what would be the initial value? Well, just like if you don't have a number in front of a variable, we understand that it is a 1. So our initial value is 1. The base, like we just saw, is going to be 2. Since that base of 2, that's greater than 1, so that's going to be growth. Now we need to know what is our rate. Now this isn't a decimal number, and that's okay. We're going to use the same process. Since our base is bigger than 1, we're going to say 2 minus 1 is 1. Okay, well, I want to know that as a percentage. This is like 1.0 or 1.00. So if I want to know that as a percentage, I can take 1 or 1.00 and multiply by 100, and that gives me 100%. So something that's important to note here is that if you have your base of 2, that means you're multiplying by 2 over and over, so you're doubling the initial amount. If you're doubling something, you're increasing it by 100%. All right, and then example 4. This one's similar because it does not have the parentheses. It's not written in the traditional form, but we can see that 0.73 is what has the exponent. So we can write y equals what times 0.73 raised to x. Well, again, if there's nothing written there, we're going to understand that it's a 1. Now our base is the number that had the exponent, which is 0.73. Since 0.73 is between 0 and 1, that's decay. And to find the percentage of decay, we're going to take 1 and subtract 0.73. So that gives us 0.27. And 0.27 as a percentage, we're going to multiply by 100. So that's 27%. All right, we're going to move on to some mixed problems that you might see on an exam. So the function f of x equals 5 times 2 raised to x represents the number of bacteria f of x growing in a culture after x hours. How many bacteria are in the culture after 3 hours? So x in this function represents hours, and we want to know what is the total amount after 3 hours. So we are going to plug in 3 for x. So f of 3, meaning we're plugging in 3 for x, is 5 times 2 raised to 3. Now we can simply type that into Desmos. That means 5 times 2 raised to the 3rd power, which is 40. So that is 40 bacteria. In number 6, we have 2 different functions. One of them is exponential. So the one that's exponential will be the one that has the x in the exponent spot. And then the other one looks a lot like y equals mx plus b. So that one's actually linear. Now our question is asking us, what is the value of f of 4, meaning we're going to plug in 4 for x in the f of x function, plus g of 3, meaning we're going to plug in 3 for x in the g of x function. Okay, so we are just evaluating here. We're substituting numbers in for x and then evaluating, plugging it into Desmos. So let's start with f of x. So f of x, that top one, we're looking for f of 4. So f of 4 means plug in 4 for x. And then we evaluate. So once we've plugged in 4 for x in that exponent spot, we just type that into Desmos. 64 times 0.5 raised to 4. And that gives us a value of 4. All right, then we have g of x. Well, we wanted to find g of 3. Now, g of 3 means plug in 3 wherever you see the x. So 20 times 3 plus 12. And we're going to simplify that by just plugging it and evaluating it in Desmos. So 20 times 3 plus 12 is 72. So f of 4 is 4. Then we're going to add what we got for g of 3, which was 72. 4 plus 72 is 76. And that is all. In example 7, we have one exponential function, and we want to know to the nearest whole number, what is the average rate of change? So average rate of change we haven't talked about since linear functions, but it's the same process. The average rate of change is the change in y over change in x. And that's the same as taking y2 minus y1 over x2 minus x1. And typically, we would do this in a table. So this question is asking us to find the average rate of change from x equals 0 to x equals 15. So let's consider if we had a table, we would be looking at when x is 0 and when x is 15, and we would be subtracting those y's, subtracting those x's. So what we can do here is find what is y when x is 0. Well, f of x, remember, that's the same as y equals. So we want to know if x is 0, what would that simplify to be? What would y be? So to find that, we can take and plug in 0 for x. All right, so for this process, we're going to take 50,900 times 1.03 raised to the power 0. All right, now there's something special about raising something to the power of 0. It's always equal to 1. So that actually simplifies to just be 50,900. I'm going to move this over so we have a little more space to write. Okay, so that's our y when x is 0. Now we're going to repeat that process, but we want to know if x is 15, what is y? So we're going to take 50,900, 1.03 raised to the power of 15. So in Desmos, I'm just going to backspace and make that a 15. Now we have a very large number. That's 79,300.54. I would just say 54 because we're going to round to the nearest whole number anyway. Okay, so now we want to know that average rate of change. So to find our average rate of change, we are going to take our change in y. So we're going to subtract 79,300.54 minus 50,900 over, so this is our change in y, over our change in x, which would be 15 minus 0. All right, so just typing this in real quick, we're going to get all right, so if we simplify that, that's 28,400.54 over 15 minus 0 is 15. So now we're going to divide 28,400.54 divided by 15. So that's 1,893.36. So we are going to say that is 1,893 rounded to the nearest whole number. Number 8. Okay, a club began with 3 members. Each month, each member brought 1 new member. Which function could be used to determine the number of members X months after the club began? So to really get a good idea of what is happening here and to see this pattern, since our options have some linear functions and they have some exponential functions, we need to know if this is linear or exponential. And the best way to see that is by creating a table. So if the club began with 3 members, that would mean after no months, so the initial value would be 3. Okay, so if X is months and Y is members, okay, after no months, so when it started, it had 3 members. Then after 1 month, if each of those members brought 1 new person, how many members would there be? Right, so think you are part of the 3 members in the club and each of you brings 1 more person. Then that month you're actually going to have 6 people. All right, well, what if the next month you and the rest of the 6 people in the club, you guys all bring another person? Well, that's going to make it 12 people. And in the month 3, if all 12 of those people also bring someone each, that would be 24. So this pattern is actually changing by multiplication, right? It's doubling. So if it's doubling, we can rule out linear altogether because it's exponential. And then all we have to do is determine the initial value, and we already know that our base is 2 because it's doubling. So it has to be D. The initial value, the original amount was 3 members, and it is doubling, so your base is 2 each month. All right, number 9, which choice could be modeled by a linear function? Okay, so remember a linear function changes by adding or subtracting the same amount over time. So A, the amount of money in an account after X years earning 4% interest compounded annually. Well, this 4% interest compounded annually, that means that it's increasing by a percentage, by multiplying. So it can't be A. For B, the monthly cost to use a cell phone for X minutes at a rate of 4 cents per minute. Well, if you're increasing by 4 cents per minute, then you're continually just adding that amount. You're not adding a percentage, you're just adding 4 cents. So our linear function is going to be B. Let's look at C and D just to explore those. So the height of a ball after bouncing X times, if each bounce reaches 2/3 its previous height. Well, because it's reaching 2/3 its previous height, that is multiplying by 2/3. And D, the amount of radioactive material remaining after X years when the decay rate, or when decay occurs at a rate of 30% each year. Well, because you are decaying, you're actually keeping only 30% of that, so you're multiplying by 0.30.